Does there exist a first-order differential equation with continuously differentiable right-hand side on the whole plane, such that all its solutions are odd functions? Well, now this is a bit tricky, so you need to kind of really understand this material very well to be able to solve this. So let me try to explain how you can arrive to the solution if you try to reason logically. Well, all its solutions are odd functions. Well, if all solutions are odd functions, so what is so special about odd functions that we can apply here? Well, first of all, maybe let us recall the definition of an odd function. So the definition of an odd function, so y of t is an odd function if y of negative t equals minus y of t. That's the definition of an odd function. Well, which odd functions do we know? Well, y equals t is an odd function. Y equals t cube is an odd function. So y equals sine t is an odd function. So maybe let us try to plot a few odd functions to kind of understand where it's going on. So y equals t goes like this. Y equals t cube goes like this. Sine t goes like this. I don't know, negative t goes like this. But I think you can kind of see the pattern. And here, the kind of the property that is important is that all these odd functions, they pass through the origin. So let us try to figure out, is it true? Is it true? Is it true that if a function is odd, then it must pass through the origin, that we must have that y of 0 equals 0 if y is an odd function? Well, let's see. So is it true? So we know that y of minus t must be equal to minus y of t for all values of t. So in particular, it must be true when t equals 0. So y equals negative 0 equals negative y of 0. But negative 0 is same as positive 0. So y of 0 equals minus 1 of 0. So moving y of 0 to the left-hand side, we get 2y of 0 is 0, which means that y of 0 is 0. So yes, it is true that if that every odd function must satisfy the property that its value at 0 is 0. All right, so every solution of this differential equation has the property that y of 0 is 0. But at the same time, we know that y of 0 equals 0 is just a particular initial condition. So we could have a different initial condition. For example, y of 0 is 1. And according to the Picard-Lindelöf theorem, there must exist a solution of this differential equation with the property that y of 0 is 1. But we just proved that it doesn't exist, right? So if all solutions of our differential equation are odd functions, it means that the initial value problem, y of 0 equals 1, does not have a solution. But if it doesn't have a solution, then this is a contradiction to the Picard-Lindelöf theorem, according to which every initial value problem must have a solution. So this concludes the proof of this question.